So, uh, let me introduce again myself. My name is Muhammad Farah Akbar. You can call me Muhammad Farah Akbar. Okay. Now I'm as a reservoir engineer and petrophysicist at MOL Group Hungary. Today I would like to give you some overview about reservoir rock typing and also with some of the case studies that I already implemented in some case studies in various subsurface work in different continents. So the title is Reservoir Rock Typing for Better Reservoir Characterizations. We use my laser point. So it's a little bit introduction. It's already mentioned. Actually, I come from Indonesia. I was graduated from the Petroleum Engineering Department from Institute of Technology and Science Bandung, Indonesia. And after that, I continued my master at the University of Miskolc at Petroleum Geoscience and Engineering programs. I started my career as a reservoir engineer consultant at LAPI ITB and then continued with the Lamicus. And also, I was also as a lecturer assistant at Bandung Institute of Technology and Science. And currently, since 2020, I joined the MOL Group Hungary as a reservoir engineers, but also as a petrophysicist support for several projects. I won several international awards regarding my papers regarding rock typing, and mostly it's related with the reservoir rock typing implementation and also connection with the other physical responses that I will explain today in my presentation. So the rule of the presentation today of the webinar, it's simple that the committee said it will be recorded and it will be published in the YouTube channel from the Skill Up training. Also, it will be presented more or less 1 hour, around 45 minutes presentation and 15-minute question and answers. Please mute your audio and camera during the presentations. So let's make a connection is better as well. And the chat is available if you wanna drop your question and some things that the host will manage for the question and answer. And please make the question and answer after the presentations. For the agenda, I make the 2 sessions. Session 1 is about introduction of the reservoir typing, and the session 2 about the case study and the comparison between the rock typing that I want to introduce you, called so-called the porphyrometry and pore structure rock typing, and how it's compared with the rock typing like pole zone indicator or hydroflow units, Lucia, and so on. So let's start. Archie in 1950, it's already introduced about the rock typing itself. The rock types explained by Archie, it's always used in various, how can you remove the, okay. It's the rock type itself, it's explained as the rock deposition deposited in under the similar conditions of the geological process, sedimentological process, especially with the similar diagenetic process as well, which resulting the similar unique porosity permeability relationship, and also follow with the capillary pressure profile, and also the water saturation, until it's given the height above free water in reservoir with the special characteristic. In the simple way, we usually have the rocks like from the coarse to the fine grain, for example, of the samples. And then from here, when we have a bigger pores, usually we have a good porosity, and the permeability, when we plot the porosity permeabilities, will be located in the right corner on the upper part. Meanwhile, during the decreasing of the quality of the rock, which means that you have the decreasing of the porosity and the permeability, and also it will behave like this. And from here also, it usually follow with the gamma ray in the conventional reservoir, like a sandstone and carbonate. During the poorer quality of the porosity permeability, your gamma ray will be increasing, and it's also can explain as the flow unit that we usually say. But regarding the reservoir rock typing, It's more related with the analyzing and integrating the geological and also petrophysical data. And it's also try to connect with the engineering parameter in order so we try to connect from the geological, petrophysical, and the engineering data in order to make a better reservoir characterization for estimating the initial hydrocarbon in place and also for better forecasting and reservoir 3D dynamics. In the fact, many inconsistent rock typing in the connection to the geological phases and petrophysical properties are appeared. So that's why in here, the challenge is how to predict the permeability of the saturation Higgs model, especially in carbonate reservoir rocks. It's quite challenging. So how in this topic of the presentation, we can solve the reservoir rock typing, especially for carbonate, with a better grouping method. The last but not least, the well understanding of interrelationship of the reservoir rock typing to petrophysical properties, geological, rock physicals, and the rock mechanical properties is not have a good connection. Meanwhile, there are many kind of projects we can connect with this. So rock grouping itself, there are a lot of termination that we usually heard. There are rock types, lithophases, electrophases, rock class, spectrophases, hydraulic flow unit, hydraulic rock types, and then the reservoir rock types. And we try to explain here detail by detail, actually, that we usually know that the rock type itself, making a group of the rock having the similarity of porosity, permeability relation until with the capillary pressure data, water saturation, and so on. But sometimes they are not connected each other with the lithophases. Meanwhile, when the geologists try to make the rock typing based on the lithophases, sometimes the lithophases overlap with the data of the porosity permeability data. We also have known, like say, the electrophases. The electrophases is not represent directly to the rock physical property, but this is mostly make a grouping based on the artificial intelligence of the cluster analysis, for example, unsupervised or supervised, based on the similarity of the log responses and try to make the groups. Meanwhile, we also is very well known, we call it hydraulic flow unit. Actually, this hydraulic flow unit, it's defined mostly about the flow zone determination. We can making a unit of the rocks that connected with the similar port rock attribute on hydraulic unit. Meanwhile, for the application, saturation Higgs function and so on, reservoir rock type it's more important. And unit of the rock having the reservoir rock type itself is the unit of the rock having similar geological features and both similar static and dynamic physical properties. Okay, let's start with the simple phases that we usually know that about the carbonate phases from Dunham. Usually, the carbonate is grouped based on the depositional texture that we usually know that it's a mudstone, wexstone, packstone, grindstone, bondstone, crystalline, and so on. What is the good of this method is easy because we can simply identify from the thin section data if we have the core data. Otherwise, if we don't have the core data, it will make our interpretation is quite difficult. So that's why if we have a good complete data, let's say the thin section, the routine core data, and special core data, we try to connect the grouping based on this textural and try to connect with the porosity permeability.
Engineer Muhammad. Engineer Muhammad.
Yes.
Sorry, we have some lines on the screen. So could you please remove it? We have red lines on the screen.
I don't know who wrote this. Can you remove it? How to remove the line? I don't know why it's coming the line here. Yeah. Yeah. Okay.
Yeah, that's good. Yeah.
Okay, it's good now, yeah? All right, let's continue. In 1950, Archie also tried to develop or introduce the first rock typing. This is quite simple rock typing. They just try to plot the porosity permeability and try to see the relationship between the saturation from the capillary pressures. And from here, Archie tried to make a trend from the many kind of the formation, which is deposited under the similar environment. And he said that in the similar environment, deposition environment having a similar porosity permeability relations. And after that, he made the various kind of different line in different field from his investigation. The advantage of this method is very simple because we just consider the geological and petrophysical characteristic. But the problem is when we try to connect with the special core analysis data, let's say for the rock type, maybe especially for the heterogeneous rock like the carbonate, it will be inappropriate to use because it will be a lot of overlapping between the capillary pressure and also with the porosity permeability relations. The capillary pressure base is also can be used a really good rock typing method because in the good quality of the rock, let's say good permeability. Okay. In many cases, the capillary pressure is the good tool to make the rock typing, but unfortunately, not every single core data or sample or the wells, when we drill, we have the special core analysis data, especially the capillary pressures. The good thing that we can create it from the skull, it's make it really consistent when we are trying to create the saturation head model and also for predictive permeability. But the disadvantage, when the skull data are limited, routine core data also limited, we cannot do this kind of the rock typing. Another very common, Winland R35. This is also very common and very fast way to do porosity permeability based on our routine core data without skull data. But the disadvantage, there is potential misuse of scale data, especially for the capillary pressure distribution, when we try to make the grouping of the R35 with the grouping of the special corals. I will show you how the comparison, this method, it's not really good for the skull distributions. And also there's also the rock fabric based on the Lucia from 1983 until 1999. He created like 3 main rock fabric classes based on the grain size and the sorting, based on the petrophysical data. This rock fabric control post size distribution is really good to make a relation with porosity and permeability. This is also good for predicting this one, but the disadvantage of this method actually for the carbonate, if we have kind of the bugs or the fractures, separate and touching faults, it's potentially miss predictions will be happen, and also the potential of the overlapping in special core analysis data for capillary pressure and relative permeability data. Another rock grouping was also proposed by Lawrence. This is published also from the Gunter in 1997, how the rock grouping can be implemented by using the flow capacity plot together with the storage capacity. And from here, we can define the grouping based on this one. This is really good in order to identify the productivity intervals and also the flow corridor of the reservoirs. But the disadvantage of this method actually is ignore the water saturation and the capillary pressures. Once when we try to make the saturation head model, at least we need only one average of the capillary pressure data, and we try to distribute it. If we have quite complex reservoir properties, possibility there will be some overlapping happen during the saturation distribution based on the capillary pressure data. And also the hydraulic flow unit. The hydraulic flow unit is very common use in many kind of case study in sandstone and carbonate, where this method actually it's developed under the Cousins-Charman equation. And the rock group actually it's based on the basis of the flow zone indicator. This is simple. From the Kozeny-Charman equation, we try to make a plot between the pore geometry or RQI with a reservoir quality index, which is the permeability over porosity in the square root, multiplied 0.0314. And from here, the hydraulic flow unit try to make really good groupings. It is really good tool to predict the permeability by using routine core analysis data. But the problem is when we try to use the hydraulic flow unit for the saturation distribution, it will make potential misuse, especially for the carbonate reservoirs. So that's why this method, it should be taken carefully when we try to create the saturation height model based on the rock typing from the hydraulic flow unit. This is also very common use, the cluster analysis, electrophases, even supervised or unsupervised. This method actually is just a statistical base, and it depends on the input that we put into the training. This method is usually can be used for the permeability predictions and also for the rock type or clusterings based on the log responses. And from here, actually, this is good when we try. If you have a good core data, a lot of sample for training, and then you can distribute the rock group based on the training from the core data. And after that, when the distribution is met, and then you can do any further evaluation like saturation height model or capillary or permeability prediction from this. This is very fast, accurate distribution as well in uncore interval if you use a supervised case. But if you use unsupervised case, sometimes it's really wild to use because it depends on the input that you to implement into the processing, and it's created a really wild result if you cannot control your log input into your models. There is advantage also. It can be issues in the skull data, and there is no physical meaning sometimes in this model because mostly it's run based on the statistical approach. And inside of this approach as well, there are a lot of options which can make a different result in every run that you created. And the last method that I want to explain is about the pore geometry pore structures. It was developed firstly by Permadi in 2009. And then Wibowo and Permadi in 2013 tried to transform better models in order to create the rock type curve in order to make it easier to define rock type. The basis of this rock type is the similarity of the pore geometry and pore structure. Actually, it's plotting like the similar of parameter like flow zone indicator or hydraulic flow unit methods, which is we call it RQI. But the difference is the x-axis, we call it as a pore structure, which is the parameter of permeability over porosity power of 3 as the x-axis. And this method actually is really good. We only need the routine core analysis data. It is fast and also relates to geological characteristic. We also can be used for the permeability prediction, confirm the J function as well, and maybe the geonic study until the result of NMR porosity and permeability. Disadvantage have to use the standard type curve. It's just quite difficult to make the line, but from the study in 2013, the type curve is available as well. So you can really to use this type curve in order to define the rock type with the robust quality of the grouping method. Why this PGS is good? Because it's collected from different kind of core data from the sandstone, let's say around 3042 sandstone data from around 7 basins in Indonesia, and also it's around almost 2000 carbonate sample as well from different basins. And from this data, it's not only connected with the routine and special core, but also try to connect with the geological description from the thin sections, from the SAM, and also from the XRD. And from here, the study was integrated the petrophysical, geological, and engineering study, and tried to implement it the petrophysical static and dynamic model as well. For example, in 2017, she created how the capillary pressure can be distributed in each rock group, and from here, not only the capillary pressure into the jet function transformations, but also it confirmed with the really beautiful textural of the geological is very consistent from the clean sands until the shelly sands it's created here. And from this, he tried to collect it with the pore geometry and the pore structures, plotting, and after that, the rock type is generated. This is also work with the carbonate. For example, we have this capillary pressure data, and I will generate the capillary pressure based on the rock groups. And from the rock group in each rock type, we can see that from the textural point of view, the pore type here is much bigger pore type. During the decreasing of the quality of the porosity and permeability, it's also confirmed that the irreducible saturation is turning to the right side, and also it's following the more tighter rocks that we can see from the thin sections. So what is the physical background actually from the PGS? Actually, it's starting from the Kozeny-Charman, where is the permeability is the function of the porosity, tortuosity, pore shape factor, and specific surface area. Through the arrangement and the modification of the equations, finally we can create it in the fractal models, which is the power law model of the porosity permeability relations, where we call it this parameter as the pore geometry, and this parameter as the pore structures, while the B, we call it the exponent of the self-similarity. When we try to plot pore geometry and the pore structure on log-log rock graphs, it will create the straight line. And the B represent of the complexity of the pores, maximum 0.5. It means that you have strike capillary tube. But in the real subsurface rock, in porous rock, it's almost impossible or rarely found having the strike capillary tube behavior of the rock. Instead of this, in the interconnected pore, it will behave like a tortuous capillary puddle. And after that, the pore shape as well is not like a circle. Meanwhile, it will be in irregular shape. So that's why the B should be less than 0.5 and the tortuosity should be more than 1. So in a simple way, when you have the porosity permeability data and we plot in pore geometry and pore structure in the log-log scale, and you will see this kind of the rock groups, for example, this green, browns, and the reds as the one groups. What is make it different? When you have a 3 different slope in each rock type, it's mean then that the more complex properties of the rock you will see. The increasing of the B value, it's mean that the more poorer quality of your rocks. And what it's different in one line. If you have the higher porosity permeability in this part, meaning that you have a good porosity, the pore system in the rocks, which is the tortuosity is smaller, and the pore shape also is increasing. During the decreasing of the line, the increasing of the specific surface areas happen that you can see the more compact of your pore system, but the tortuosity is still the same. But the changing of the slope, meaning that you have the changing of the pore shape as well, the tortuosity is changing, and the more complex of your pore shape during the increasing of the B value, it's mean that the lower quality of your rocks. So from here, in order to make it easier, the pore reservoir rock type curve is made. And from here, we also can use how to define our rock typing easily and fastly. So in the session 2, I try to make the comparison between the different rock type with the PGS, how it's compared with the result. For example, here, in this session 2, I try to see the PGS compared with the other methods, some of the case study of saturation height functions, and also application and elastic properties, and it will be close with the summary. So let's see with the comparisons first. We have hydraulic flow unit or flow zone indicator methods. We have the PGS and we have rock fabric from the Lucian. We use the same rock, carbonate rock that we implemented from the study of Vibo and Permade in 2014. For example, in this hydraulic flow unit, and when we have the rock group from the core data and routine cores, and also we see our special core data with the colors here, and then when we try to transform into the J function, how we can see the overlapping between the rock groups from the hydraulic flow unit. Meanwhile, from the pore geometry structures, we can see how the consistent the grouping in each rock group, meaning that if we implemented the saturation model with this pore geometry structure, the overlapping it will be reduced and make the saturation model will be better. Meanwhile, for the rock fabric as well, we can see how a lot of overlapping happen, especially for the rocks is having a micro fractures. It cannot be well characterized. It's make the prediction either for the permeability or for the saturation model. It will be overestimated or underestimated. And what is the difference? For example, we have one rock groups from the hydraulic flow units in this magenta color, for example, and the purple and the orange. And what we see the sample in the hydraulic in the pore geometry pore structure plot, either it's said it is one rock group, but in the PGF it says it's 4 different groups. So that's why it's make the overlapping between the in every rock types by using hydraulic flow unit, because the range of the porosity in one group is really huge. Meanwhile, the capillary pressure itself is the function of the porosity, or let's say the pore throat radius, where this pore throat radius also have a connection with the porosity. So that's why having a hydraulic flow unit for the saturation model based on the capillary pressure, it will be worse, especially for the carbonate reservoirs. Another case study, which is just presented last year from me and my student, which is how we try to connect the capillary pressure data from different carbonate rocks with the different rock type method, from hydraulic flow unit, Jennings-Lucia, Windland, and PGS. And from here, we can see that how the PGS is separated very distinguished in each rock groups. It's meaning that we will create a really good saturation model with the minimal overlap. Meanwhile, for the Windland, Jennings-Lucia, even the HFU or hydraulic flow unit, a lot of overlapping happen between the groupings. Not only the capillary pressure data, we try to connect with the T2 geometric mean from the NMR core, from our sandstone data, how the PGS is really consistent in grouping of the saturation, irreducible water saturation, and also connecting with the T2. This is important because when we try to predict the permeability based on the T2 from the NMR, the PGS can lead the better interpretation or prediction of the permeability prediction based on the NMR data if we combine the rock typing method into the predictions. Another study, for example, from Akbar et al. 2016, this is also carbonate data, how the J functions in the global hydraulic element, hydraulic flow unit, Jennings-Lucia, Windland 35, and PGS, we try to compare. And it's still that in this carbonate data in Banggai Sula basin, the PGS giving a much better distribution of the rock group concerning the J function distributions. How about the permeability prediction? Is the same. We try to predict between the hydraulic flow unit and also the PGS. Actually, the result is almost the same. This is why, because as I mentioned before, the flow zone indicator is really good prediction method as well for the permeability prediction. So do with the pore geometry pore structures. Meanwhile, for the pore geometry pore structures, it's not only the function of the porosity, but also the irreducible water take into account into the predictions. And this is made a bit different between the flow zone indicators. And from the result as well, we can see the result of the hydraulic flow unit and PGS is almost the same. But from the study, the PGI is giving a much more better fitting between the measurement and the predicted. But what happens if you just predict the permeability by using porosity permeability relations? And you can see from the blue points in here, it's really spreaded. Just in some part we can make a prediction, but in some microfracture happen, we cannot predict the permeability in the good manner from this simple porosity permeability relationship. One thing should I emphasize why this method is good using the irreducible water saturation, because many cases of study from Vibo and Permedi 2014 from different basins, there are always a really good relationship between permeability and irreducible water saturation. So that's why when we try to involve the irreducible water saturation into the permeability predictions, it will give a better result of the permeability prediction result. Not only that one, we also can have a good better prediction in the saturation height model. In case of the implementation, in the case study, it was one of my publication in 2016 about estimation of fluid-fluid contact and the transition zone, which is a case study of low contrast resistivity zone. So why the saturation model? It's important because in 3D model, even the static and dynamic, the saturation is developed by the saturation height model. But sometimes it's difficult to understand the capillary pressure behavior. So I start with introductions. We usually know that when we put our tissue or the paperwork into the waters or the liquids, the liquid will try to move from the bottom into the height of the paper itself. So how we can understand how the capillary pressure itself? So this is our, for example, this is our reservoirs, this is our water levels or aquifers. When we touch this, we will say this is our oil water contacts, this is free water levels, and this is, we call it as oil water contacts. And then during the increasing of the heat, we will have the transition as well from years, and we can see the transition of the waters here. It's related with the capillary pressure data. When we touch this one, we call it this is the end of the transition zone, and above this is the free air that we usually connect it with the irreducible water saturation. In a simple way, since we have the height function in here due to the capillarity index, so that's why we can transform the capillary pressure itself into the height function. And also, if you use the J function, let's say in the form of the power law, and then after that we can estimate it, the water saturation as the function of the height. So this is what I explained in the beginning. We can jump into different one. So the capillary pressure in each rock group has a different behavior in the different rock groups. For example, if you have good quality of the rocks, and then we have capillary pressure in the left, more to the left. But if you have the worst quality of the rock, the capillary pressure will go to the right. And from here, we can define the saturation functions based on the capillary pressure, which distribution based on the rock type. This is one of the example in sandstone, for example, when we try to create the saturation height functions from our core data. There are 5 rock types were established, and the group 1 in here, the green, is the best rock groups. And from here, we try to see how the permeability, irreducible water saturation from the skull data is really beautifully separated. And not only that one, every rock group has a specific irreducible water saturation, which is not overlap in each other. And it's also represent to our capillary pressure data. And after that, we try to implement it as well in order to create the rock type along the wells from these equations. What happened? In this case study, actually, we have typical of the sandstone data. We have low contrast, high resistivity rocks, and we do the test. It was around 1,000 barrel oil per day with the water cut of 6%. And the problem is, if we have the water cut produced during the test, it should be we are in the transition zone. But the problem is, where is the contact of the fluid? And so from here, we try to solve how we identify the capillary pressure data as the function of the capillary pressure, and also with the J function. By the substitution of this equation, we can predict the height from the contact and also from the irradiation from the water saturation itself as a function of the J function. So, for example, in this part, in our core data, there are several rock group was created, which is 5 rock groups is created. However, we have skull data here. It's only available from 2 rock types. We don't have another skull data from the other rock types. So that's why we have to predict how to define this another capillary pressure data of this rock type. Once we get this prediction of the capillary pressures into the J functions, and that we try to predict our saturation function based on the J function that we created from here. Meanwhile, for the permeability prediction last time, we used multivariate regression, which is just quite robust result from our prediction based on this method. In terms of the oil water contact and free water level estimation, we use the ratio of the relative permeability data. We have the well test data, and we try to transform our well test data into the permeability ratio between relative permeability of water and relative permeability of oil. We have the water cup from the well test, and we have the fluid properties from the PVT data. And after that, we try to see to understand the saturation in each testing point. And from here, we try to identify the free water levels. Once the free water level is created, we can define the saturation height function from these models. This is the result of the porosity and permeability predictions, and this is the rock type distributions, and how we generate the saturation height model based on the rock groups. And from here that we already defined the oil water contact and free water level from the previous slide, and the permeability prediction based on the multilinear regressions. The rock type is established in the track 9. And finally, we distribute the water saturation for this case study. Because when we try to make the water saturation based on the resistivity, it's very hard because there is no difference between the hydrocarbon and the waters formation. This has happened because the formation water at that time, it was a fresh water, makes it's quite difficult to differentiate between the resistivity in the hydrocarbon and the water intervals. Another case study also can be implemented in 3D model. This is, for example, how the saturation is built in the different models, and we can transform the saturation function based on the irreducible water saturation from the capillary pressures, and it's follow in different rock types. Another PGS rock typing, it is also work for characterizing the elastic properties. It is published in one of my papers, which is in 2019 in Calgary, Canada. This approach actually could help how the elastic properties connected with the pore geometry and the pore structures, and how we try to connect with the other parameter related with the PVF velocity. So the background is why we use the PVF velocity in this study, because the PVF velocity is really important data. Usually we use the wave velocity. It's coming from the bigger scale, for example, the seismic. We have from the well basis as well from the sonic log, VSP check shots until the core data. But in this study, we do the experiment, the core data, and from here actually we have a different frequency that we have to consider when we do the further evaluation to use this method. The study workflow, it's coming from porosity, permeability, and PVF velocity with the quality factors, and we created the rock typing based on the porosity and permeability data. And from here, we try to make a connection between the PVF velocity with the porosity together with the attenuation factor or quality factors here. And after that, we try to involve the critical porosity concept in order to make the correlation between the critical porosity, the porosity permeability. And then finally, we try to make a prediction, the PVF velocity prediction, or the porosity permeability prediction as the function of the critical porosity and PVF velocity, and also for the attenuation factor from porosity permeability data. I use quite wide, a lot of data from 120 sample, PVF velocity, permeability data from Middle East, Southeast Asia, and Australia. And you can see how the heterogeneous porosity permeability from this carbonate data, because it's not coming from one field, but it's coming from a different field. But the good thing we can see this normal usually that we can see that porosity and PWF velocity have the good relationship on it, but we never try to connect the PWF velocity and permeability because it's very complicated to characterize. We also have the sandstone data from the different basin as well, from UK, from China, and until from the US. And the similar behavior can be seen that we cannot make a good relation between PWF velocity and permeability. So what happened? In the carbonate data, for example, we created a rock type group from here, and we try also consider the textural of the rocks and how the description has a really good connection. Let's say in the good rock type, the dominant of the pore type is the VOX, connected VOX. Meanwhile, during the decreasing of the pore type, which is the increasing number of the rock type, it's having the poor quality, which is mainly dominated with the waxstone and packstone, with the moldic and intraparticle pore types. So what happened? That we saw the PWF velocity and permeability is really spread relationship. But what happened if we make the groups? Actually, when we create the group based on the PGS, it's really beautifully separated in each rock group. And from here, it's easily for us to identify and characterize the property of the rocks. And from here, that, for example, that from these results, we can see, okay, the physical we can post because we have a limited time at this moment. Yes, from here we can see that PWF velocity has a really good relationship with the pore geometry and pore structure. So that's why in the later, when we have a good permeability porosity prediction, we can predict the PWF velocity once we don't have the measurement in the wellbore. This is also the same for our sandstone data. The result is very beautiful with the separation of in each rock group in PWF velocity. And from here, we can also predict later the PWF velocity as the function of porosity and permeability. Another thing, since we know that PWF velocity is the function of bulk modulus and shear modulus, and based on Noor in 1995 and Mafko et al. In 2009, how the critical porosity concept was based, and we try to substitute equation 2, 3 into the equation 1. And finally, we can make the new equation to predict the porosity based on the PWF velocity and also density, which is, we call it as the acoustic impedance. Once we know that if the porosity has a good prediction with the acoustic impedance, later we can also predict not only from the well logs, but also try to connect with the seismic parameters. And from here, we try also to predict the permeability from the PWF velocity, since we know the cosine is the function of the porosity and specific surface, and the specific surface can be predicted as well from the pore basis porosity permeability, and the constant based on the Mortensen 1998 also can be estimated based on the porosity. And from here, when we try to connect the specific surface area as a function of the PWF velocity, and then we substitute the equation, and we can predict the permeability from the acoustic impedance as well. And what happened? How to define the critical porosity? When we have the Voigt upper bound and Reuss lower bound, we try to connect them with this every rock group that's created from the PGS. And every rock group having the critical porosity from the different rock groups. And from here, we also can predict later when we have the critical book models at the critical condition based in this equation. And finally, we can predict the porosity once we already know the critical porosity and also book models at the critical conditions. There's also the already published from the Noor papers about the critical porosity, which define in different kind of the range, which is also connected what we have from our study. This is the result of the porosity prediction, either for the carbonate and sandstone with the relative error is quite low, together with the permeability prediction as well. From the PWF velocity, it's still promising to be implemented. Then one of the application was used as well from the Wijaya, it's with the preprint in carbonate samples. How in the logs from the sonic porosity from the Wiley can be corrected by using the critical porosity. And from the study also proved that the acoustic velocity is not linear and in different pore structure and pore geometry, which is related with the rock types. And from here as well, the calculated sonic porosity exceeding the total porosity, if you see from the red color in here, from other log measurements. So that's why the correction is needed. And the critical porosity, one of the good method to define the correction of the porosity estimations. Another study, it's related with related to rock mechanics as well, how the bulk modulus, shear modulus, Poisson ratio, and the Lamy constant have a really good connection with the pore geometry data. And from here as well, that the elastic property can be connected with the tortuosity and the pore shape factors during the investigation, and this behavior also connected with the specific surface area in each rock type. Another study also that I mentioned about T2 NMR, this is also very well connected with the porosity permeability relation from the pore geometry pore structure rock typing. So as a conclusion, I think we are reaching our time. This pore geometry pore structure rock typing is really important for the petrophysics, reservoir engineering, petroleum geoscience, rock physics, geostatistics, geomechanic possibility that PGS rock typing has to develop a beta saturation model and also the permeability predictions, strong connection between T2 NMR for geometry and pore structure parameter as well. And also for the petroleum geoscience, but PGS rock typing is very in line with the microscopic geological features from the grain size, sorting, packing, etc. And this is very well correlated between the PGS result and the geological rock phases. And what happened, it for sure improved the static model quality, especially for the saturation modeling. In case of the reservoir engineering, it will also assist to distribute the capillary pressure and relative permeability data for reservoir simulations. And also this will improve the accelerate the history matching process and the quality. For the geostatistics, there is opportunity to connect with the clustering method, artificial neural network, self-organizing map, and also possibly support the interpretation result of the well-logging inversion. And for the rock physics as well that I mentioned before, the porosity permeability prediction based on PWave velocity and critical porosity can be met. And also possibly to support the seismic inversion as well to well predict porosity permeability distribution in spatial spaces. In terms of the geomechanics that I showed also in my previous study, it's well understood. And in terms of the connection between the rock elastic properties with the PGS parameters. Do we still have time? Because I have something that related with the reservoir rock typing in fracture basement. If we have a time, I will talk a little bit how we created the rock typing in here. If we don't have time, I think we can stop until this and we can go ahead with the question and answer.
Yeah, I think you can continue.
Okay, great. So actually, this is one of my newest papers related with natural fracture basement, how we create the rock typing in this natural fracture basement. So this paper was chosen as one of the best paper in PWLA conference last time in Stavanger in June. So what I'm going to share you here, this is one of the case study in Hungary. We have a really complex structure of the fracture basement, not only the complex of the rocks, but also the complex of the oil itself. We have really high pour point oils, it's frozen in the surface. We have the pour point on 43 plus degrees Celsius. And from this trial, we try to connect it. We have really good core data from many core data. You can see that 19 wells have a port, but only 9 wells with the core measurements, unfortunately, because the core is broken when we're taking the fracture basement core sample from the rocks. We have quite good porosity permeability data in here, even though it's not really common behavior because the porosity is less than 10% mostly, or in average it's around 4%. But the permeability is up in Darcy. Even until the well test, we can see the permeability is up to 70 Darcy, which is really, really high permeability. And from here, actually, what we try to do, we try to make the rock groupings. It's quite different because in the fracture basement we have a really minimal matrix distribution. What we try to do is how to differentiate between the macro fractures, micro fracture, and the shield fractures by combining many kind of the log responses, including the image logs data. What we try to do in this case study, because we are in the old and mature field, we have very limited image logs, no production logging, no full wave sonics. What we have is just conventional logs. We try to connect how the presence of the fractures related with the conventional rock, and we try to understand every kind of the log responses in order to identify the fracture presence. Since the log responses is really depends on the vertical resolution, so if we have higher vertical resolution, it's more sensitive to the fracture presence, but it's not something like that. So what we try to do, we have macro, micro, and unchanged rock or unfractured rocks, and this is what we need to identify because the storage itself, the flowability itself is coming from the fractures. So that's why to create the rock groups or rock typing from this kind of the rock, it's quite a difference. But we need how we identify the macro fractures, the micro fractures, and the unchanged rock based on the log responses and also supported with image logs. And this is the ways we define when we have a good image log data, we try to train with the gamma ray intensity data, for example, in here, and we try to make some logic as well, the simple logic. And by combining this data, we can identify the macro and micro fracture along the fracture class. But what happens if we don't have density and gamma ray data? We try to connect the other log responses based on the self-organizing map from the supervised learning. And from here as well, we can identify how's the learning from different wells and the log responses impacting the good prediction of the fracture itself. When we make a good prediction and then we accept it for the further evaluations. What happened? How we can validate it? When we already distributed our fracture behavior, which is related to fracture class in here, we try to connect it with our flow test data. In here, we can see whenever we have the red color, which represents the macro fractures class, it's giving a flow. And from this well test, for example, well test number 1 and 7, we can have the flow, the oil up to 74 meter cubes per day oil. Meanwhile, we also have the red color, for example, here we have the good core data, and it is confirmed as well from our core. We can see a lot of open fracture as well, which supporting to the flow corridors of these sections. And we also have this sample here. We have the rock types of the red colors, which is the macro fractures. This is also showing the flow around 25 meter cubes per oil. Meanwhile, in here we have the blue colors. When we have the test, there is no flow test, and we can say that this is just the protolith or unfractured rocks, or even the fracture which is filled by the materials of the rocks. Even though we only have SV log and the resistivity log, we still can predict the fracture behavior from here. And we also try to confirm not only from the well test, even from our core data, it's confirmed from the upper, for example, a lot of red colors, so a lot of fracture present as well from our brachiated intervals. But during the deeper of the wells, the red color is disappeared, which is only microfracture is showing. Yes, what we can see from the core itself, from the thin section, just the microfracture is exist. Until the deepers, most of the fracture are filled by the calcite itself. So that's why there is no flows coming from these interval contributions. What happened when we already have this rock type, we try to distribute it spatially in 3D models. What we have to do, we combine the fault zone system with the phases together with the geomechanic properties until we distributed the phases of the fracture itself or the rock class in the spatial distribution that you can see the macro fracture with the red colors, the micro fracture in the yellow colors, and the gray colors is the unchanged rock or the protolith. And what happened when we try to implement this method as well? By using our assumption in relative permeability and capillary pressure data, since we don't have these measurements, when we created the model as well, and we can create it how the good quality of the history match was created in the field or even in the well basis. And from here, this method is really improve the quality of the static and dynamic model until we define the new proposed well in this area, which is located in this part. And after we drilled, we got the image log. We also considered the seismic fault likelihood from the PTSM model volume. And yes, we can see a really beautiful discovery of the well. And from here, that the prediction as well, it's really have a good connection between the logs and also our 3D models, even for the porosity and the saturations. And finally, can produce the oil. This is the oil. It's like a black anaconda, which can be produced around 880 barrels per day in this mature field. So this study, for sure, it's improving the quality of the fracture basement evaluations and also for the rock typing until the forecasting, until we propose the new field development that we created, that we implemented in the early of this years. One thing is good as well from this model. For example, we have the well number 7, which is just drilled, and we have another two horizontal well. You can see in here, it is a dry well. And what we see in here, that there is no red color was penetrated during the drilling. And you can see as well from the image log, almost only 4 fracture can be identified from the image. Meanwhile, in well number 6 and well number 7, we can see hundreds of the or even thousands of fractures. It's identified from the resistivity image and also from the acoustic image. So that's why this method, it was quite robust in order to identify the fracture distribution in the fracture basement reservoirs. I think that's all from my presentation today. Thank you very much for your attention. I'm open for the question and answers, and I give it back to